So we're happy to have Barış Kartal from Princeton University talking about algebraic torus actions on Fukaya categories.
Thanks. Thanks for the opportunity to speak here. And let me make this full screen. Yeah, so the title that I gave originally was a bit longer. I thought that would be catchier, but I think that's wrong. Yeah, so I'm going to talk about constructing algebraic actions of algebraic tori on Fukaya categories and how to use this to deduce conclusions about the Floer homology groups under symplectic isotopies that are non-Hamiltonian. So this is an overview. So, I will start with some motivation, and we'll try to emphasize the geometric side of the story as much as possible. So, okay, start with a closed symplectic manifold, and if you have a closed one form alpha, you can define a symplectic vector field X alpha by this rule here, like negative interior product with X alpha gives alpha, and I will use the notation phi alpha t to denote the flow of X alpha. So if you have nice Lagrangians, tautological, unobstructed, etc., you can define their Floer homology, and you can define the Floer homology of L with phi alpha t L prime. So this gives you a family of Floer homology groups that's parameterized by T. And more generally, if you have an element of the first cohomology with real coefficients, then you can pick an alpha that represents this class, like a closed one form alpha that represents this class, and you can you can define phi v to be phi alpha 1. So this is well defined up to Hamiltonian isotopy, and you can get a family of Floer homology groups, HF L phi v L prime. Okay, so this is parameterized by the first cohomology. I'll soon enrich this by adding unitary local systems. Okay, so here's an example. This is not an example of the theorem that I'm going to speak about, but it's a counterexample to the theorem. What happens if you don't put the assumptions? So start with the two torus, okay, and so pick L to be one of the longitudes here, and those are the vector fields, symplectic vector fields corresponding to the one forms dx and dy, and then the Floer homology of L with phi v L prime is rank 2 after if an integral, a multiple of 2, after a full rotation or twice full rotation, etc. So it becomes rank 2 when V belongs to Z cross R. Here I am identifying the first cohomology of M with R square, and it is 0 otherwise. Let me, do you still see my screen? Because I lost it. So I'm gonna draw something. Sorry. Yeah. Okay. So here is a picture. Here's the first cohomology. This is dy axis. This is I identify the first cohomology with R square, and Floer homology groups are non-zero on this blue line here, and here, and here, and here. And it's 0 everywhere else. Okay. And in particular, if you restrict to the this axis here, in particular, if you restrict to the axis here, the support of the Floer homology groups is the integers. Like it becomes, this family becomes 0 everywhere else other than the integers. And at integer points, it becomes rank 2. So in particular, you can, this is not a nice set in the sense that you can define this using, I'm blocking this up. this is not an algebraic set. This can't be defined using some polynomials or polynomials of x and e to the x. Okay. Questions so far? Okay. Let's see. So I will keep introducing the setup slowly. So let's extend this by local systems. It's just gonna be, I care a lot less about the local systems here, but it's gonna be more convenient to extend this using unitary local systems. So throughout the talk, lambda will denote the Novikov field with coefficients in C and with exponents in R. And I will use the notation GM to just mean the multiplicative group. In other words, it's lambda star. And U lambda is the unitary group inside lambda star. In other words, it's the set of elements with t-adic valuation 0. Or more concretely, it is A plus, it's like a non-zero constant in C plus higher powers of T. It's a subgroup of GM. This is what I will call unitary group. And for any unitary local system, like a global defined unitary local system, you can restrict to L prime. And you can define the Floer homology twisted by this local system. You can have HFL, comma, L prime, psi restricted to L prime. And so I think I'll make a notational clarification soon, but I can identify the multiplicative group with R cross U lambda as a group. The identification given by sending T to the R times Xi, where Xi is the unitary element here, to the pair R comma Xi. So I'll use this identification. This is an identification as groups. And that gives us an identification of the first cohomology groups. Like H1 MGM is isomorphic to H1 M comma R cross H1 M comma U lambda. And to be more explicit, you can pick a basis of the first homology, and you can, can write the elements in the first group here as T to the Vi, Xi1, T to the V2, Xi2, etc. And you can send this by collecting all Vi's on one side and all Xi's on the other side. And I will usually use the notation Z equals T to the V Xi. And I will use phi Z of L as, I will use this notation, phi Z of L is defined to be the pair phi V of L, comma, Xi restricted to L. And you can now define the Floer homology of L with phi Z of L prime. This is, in addition to phi V of, applying phi V to the second component, this is twisted by the local system, the unitary local system. So just a notational clarification, when I talk about this, H1 of mu lambda, etc., I assume that it's modeled by the torsion part. So it's a connected group. Okay. So far, this is just a set theoretic family of Floer homology groups. But if you are familiar with family Floer homology, you expect to fit this family into an analytic sheaf, but not an algebraic one. That's what the torus example has shown us. And the question is it ever algebraic? And that's basically what I'm going to talk about. So that brings us to the theorem 1. So for today, I will assume M omega is negatively monotone and it is integral and strongly non-degenerate. Strongly non-degenerate is a term that I made up for the talk. I will explain what it means. And I assume L and L prime has, are tautologically unobstructed. They have well-defined Floer homology, etc. And then there exists an algebraic coherent sheaf, or more precisely, a complex of such, over the algebraic torus H1 MGM. That whose restriction at Z gives has the cohomology given by this Floer homology group. Okay, so that's the main theorem. Any questions? quick remark. I won't tell why, but if M is Weinstein, L prime are compact, the theorem still holds, but requires, I shouldn't say other techniques, but maybe further techniques. This is related to infinite dimensional Floer homology groups appearing in the Fukaya category. And I'm going to present a bunch of corollaries of the theorem that are more geometric, that look more geometric, I don't know. So first corollary is, you have this family of Floer homology groups. You can just focus on set theoretic family at this point, parameterized by the algebraic torus H1 MGM. Okay, and the dimension of such a thing is constant in Z over a non-empty Zariski open subset of the algebraic torus. That means you have a bunch of polynomials, a bunch of regular functions on this variety, and when you remove the zero sets of these regular functions, the rank of the Floer homology is constant at the remaining points. And if you don't feel comfortable with local systems, you can just focus on the real part. I think that's still interesting. Yeah.
Hello, sorry.
Yes.
I have a question about this negatively monotone. Do you mean that the holomorphic spheres, have negative Chern number? Is that? Or?
I mean, I'm just say, yes. I mean, more like negative omega has the class. Sorry, omega has negatively proportional class to first Chern class.
Okay.
Class of omega is negatively proportional to the first Chern class.
So okay. So if there's bubbling, it could be negative sphere. I thought this created more technical difficulties than positively monotone, but maybe later it's going to show up. So it's okay. We'll see.
Probably no. This holds for positively monotone as well, but yeah.
Okay, thank
you. But when I say it holds for positively monotone, I mean I don't know examples in the positively monotone case because I need non-vanishing first Bethe number for sensible examples, and non-degenerate condition to hold. Okay. So let's see what I was saying. Yeah. So another corollary is if you have a closed one form alpha, as before, then you can consider the symplectic isotopy generated by alpha, and you can consider this real family of Floer homology groups. And claim is this is actually constant in T, except finitely many exceptions. So this is a strengthening of something that I have proven recently. Any questions? I heard someone saying something. Okay. Example, the simplest example probably is a genus 2 surface, and you take L and L prime to be this Lagrangian sphere, and you take X alpha to be a vector field that moves L towards L prime, and you can take it up to Hamiltonian isotopy, etc. That's fine. And then the Floer homology group here is non-zero when L crosses L prime, but it's going to be zero at other points. And you can ask yourself whether you can produce examples where, for instance, these Floer homology groups are non-zero exactly at 2 points, etc. And you can produce more sophisticated examples on the product, and I think on the symmetric products as well, on the product of two genus 2 surface, and on the symmetric product, etc. So here are some assumptions. So the first assumption is M is non-degenerate. What I mean is it satisfies generation criteria. And it's a technical assumption. If you don't know what it is, you don't have to care about it. It's a crucial assumption. If I was emphasizing the non-commutative aspects, I would probably say a lot more about this, but my impression is even the most educated people can actually miss where this assumption is being used. Most educated meaning most educated in the homological algebra language, and it's generated by a set of Bor-Sommerfeld monotone Lagrangians. Let's say it's a finite set. It's already automatic by this moment, but so the Fukaya category is generated by a set of Bor-Sommerfeld monotone Lagrangians. Okay, that's another assumption. And I am not going to define what Bor-Sommerfeld monotone is. It's like a balanced assumption in Paul Seidel's genus 2 paper, mirror symmetry for genus 2 surfaces paper. And I'm just going to tell the main implication of this. And this is actually crucial. So if you have something that's Bor-Sommerfeld monotone, if you have some set of Lagrangians that are Bor-Sommerfeld monotone, then once you fix the boundary conditions, there are only finitely many rigid holomorphic disks with these fixed boundary conditions on this set of Lagrangians. What I mean is, like, if you are going to count 5 cones, okay, my handwriting is really, oops. Whatever. Once you fix this boundary conditions, that you can only have finitely many rigid holomorphic disks. And people usually use this type of assumptions to set up, to put, to set the Novikov parameter to be 1. For me, it plays a more crucial role. It's just, let me mention that it is very related to the word algebraic that appeared in the title. The finiteness of the sums defining A infinity products is very important for me. And yeah, so this is the notation. I will use f of m to denote the Fukaya category spanned by the objects Li. So in principle, it's defined over Novikov polynomials, but I'm going to take it defined over Novikov field.
Okay, but Li are not the only objects that you generate.
Li are not the only objects that's generated, but this is not the big Fukaya category. That's what I mean.
Okay.
It's just the span of, this is the full subcategory spanned by Li. Okay. Okay, so the main tool is constructing an algebraic torus action. So algebraic torus is just this guy here. It's like, if you want, it's gm to the first beta number of m. And as I said, I'm modding out by the torsion part. So yes, and the action is going to be by quasi-functors. So I had this brilliant idea. Like, a quasi-functor means just an A infinity bimodule, and I had this brilliant idea that I would actually, I would not lose less algebraic people if I use the word quasi-functor instead of the A infinity bimodule. Now I'm a little skeptical of this, but anyway, let me explain the terminology here. So yeah, okay. As I said, the quasi-functor is just an A infinity bimodule. The reason I'm using this instead of functors is because Fukaya categories don't have lots of functors unless you add more and more Lagrangians. That will break our assumption. I mean, basically what you're doing is, instead of telling how, for instance, phi of z would act on the Fukaya category, you tell how, what's the Floer homology of HF, Li comma phi of z Lj. And you're also telling what this does to product structure. And if you're familiar with this, you can think of, you can compare this with Celtic Floer homology, like when you have Lagrangian correspondences, how you define functors of Fukaya category. In many cases, you have to extend the Fukaya category. So I'm not doing that. I'm just focusing on the bimodule that it defines. And I will, okay, as I said, I'm talking about algebraic actions. And algebraic action by quasi-functors just means an algebraic family of bimodules. Well, okay, satisfying an action-like property, of course. Okay, and before getting into families or anything else, let me just define it at a single point, z. Phi z I Lj is equal to, is just, you know, it has the same underlying graded vector space as the Floer chain complex of Li and Lj. So it's spanned by intersections of Li and Lj, but this differential is a bit different. So, you know, if you ignore the red term, this is just the Floer differential. I'm going to sum over the strips, so holomorphic strips with boundary on Li and Lj. That goes from, you know, a generator to another. But normally we would just weight this by T to the energy. And now I am adding the first homology class of this red line here, which I denote by partial HU. Okay, so to be more precise, to define this more formally, you would need to pick a base point and pick paths from this base point to the generators of the Floer chain complex. And then the concatenation of all of this is, you know, this class partial HU here. And you define the differential of X to be the sum that I wrote here. So, questions? Okay, hope I'm not at the point that I'm talking to myself yet.
So, like, do you just expand the lambda ring then, or to add those z variables?
Yes, but for the moment, z is just a constant. Thanks.
Like, you meaning a number?
I mean, it's just for the moment, z is an element of. Let me write this. So yeah, in the end, I will do that, but for the moment, I am just focusing on how you would define this family of bimodules for a single z. So I will define a family of bimodules parameterized by this thing here. And I pick a single z here, and that's how I define it. Is that okay?
I'm just trying to compile the expression for mu1.
Yeah.
So t is a variable we already have in the coefficient ring, so I'm happy with that. And then y is an element of this Li intersection. And then.
So, yeah, okay, maybe I should try to be a bit more explicit. So let's see. But, I mean, what I'm trying to say is, okay, so this is, you know, like, you know, this is, let's see. Okay, so pick a basis for H1. Oh, I don't know where I should write it. Okay, let me. 1 second. Maybe this is a confusing expression. So let's write in black. Okay, here, this thing belongs to H1 of M. Okay, and I pick a basis to identify this with Z to the B. Okay, and in that case, this thing here, H1MGM, can actually be defined as the spec of lambda H1, sorry, spec of the group ring of first homology of M. And there has to be another parenthesis here. Okay, and once we identify this with Z to the B, this is the same as spec of, you know, some polynomial ring, but you invert the variables. Okay, so to define, like, so you pick something from here, right? You pick, maybe Z is not the best notation. Let's write it A for the moment. Okay, you pick an A from here. You write it in this basis, A1 comma dot 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 AB.
Yeah.
And since this is an element here, you can write this as, yeah, I'm out of space. Let's see. Okay, you can write this as, do you see this part now?
Maybe if you could right. Okay, yeah, it's fine.
Okay. Okay, you can, let's see, I don't know how to write it. Okay, let's say you can write this as N1 comma, dot MB in this basis that I choose. Those are now integers.
Yeah.
And I define not Z, but that's really a non-linear way of writing. I apologize for this. You can define this thing here to be the monomial in this fixed point in lambda star to the B. Okay, so it's A1 M1, A1 to the M1 dot dot dot.
Okay.
B to the NB.
Got it. Thank you.
So if it makes you more comfortable, you can assume the first homology is one-dimensional and just pick a generator. It's like pick a generator of the integral first homology modulo torsion. And then, you can identify this partial HU with a number, and then Z is just going to be some single other element of lambda star. But as I said, like before defining the families, I'm just defining the bimodule for a single Z.
Thank you.
Hopefully that's clarifying. Sorry. No. And if you're familiar again with tilted Floer homology, I deliberately draw it in this way. So to define, to define the tilted Floer homology corresponding to a symplectomorphism, you would think instead of ordinary strips, you would think of kilted strips, where you would put, the graph of the symplectomorphism, which is a Lagrangian correspondence, over the seam. Okay. So a remark is the sums defining the Floer differential are finite because of the Bohr-Sommerfeld condition. So indeed, this is well defined. This thing here is well defined for all Z in H1 MGM.
Sorry, I have a question too about this, the loop that you take.
Yes.
If you draw the strip, like it has a boundary on Li and on phi z, right? Do you take the whole thing here or just on the path phi z?
It has a boundary on Li and Lj.
So
I didn't apply phi z. There's no phi z here.
Oh, okay. So you just take the boundary of the strip. That's your loop, basically. Is that correct?
Yes.
Okay, thank you.
I would say boundary of the strip, but for technical reasons, we concatenate them with paths. But
yes.
But think of it as the boundary of the strip myself. Yeah.
Okay, good. Thank you.
Sure. So this is how we would define the family Floer homology as well. And I'm gonna tell how to make this more geometric before getting into families, or hopefully, I think. So the sums are finite because of the Bohr-Sommerfeld condition. So this is well defined. Like if Z was the unitary element here, if it had coefficients in U lambda, then you would have this automatically. But for instance, Z equals T to the 3, where T is the Novikov parameter, we don't necessarily have this. Actually, T to 3 doesn't make sense. T to the something, you don't necessarily have this. But since the sums are finite, you have this. Okay, so here is something I already told. The functions on the algebraic torus here are given by the group ring of the first homology. This is again a polynomial algebra, but you also invert all the variables. And I'm defining the family of bimodules. The family is defined as, in this way, as Sarah was suggesting. Now I am actually expanding the coefficient ring to have the ring of regular functions on the scheme. So, this is just, you can think of this as a graded vector bundle over the scheme, over this algebraic torus. And, graded vector bundle is just, it's a bundle of vector spaces, right? And the differential varies as you vary the point. So the differential is defined just as before. So that's how you define a family of Floer homology groups parameterized by this variety, or family of Floer chain complex parameterized by the variety. The underlying graded vector space doesn't change, but mu1 changes, and the algebraic setup is this, takes coefficients in the group ring of this thing here. And to define the higher structure maps, I didn't tell you this, but to define a bimodule, you have to multiply, you have to multiply the generators of the bimodule with the elements of the ring. And you're just counting the holomorphic disks, but not only weighted by T to the E energy, but also you weight by, this red term here, Z to the class of the line from X to Y. Okay. And the previous the notation is consistent. The previously defined single bimodule can be obtained by evaluating this phi at a specific Z. Okay. So let me, hopefully I wasn't doing crazy stuff, but to convince you that this is not entirely crazy, I'm gonna tell that's nothing new actually. So the lemma follows from Fukaya's trick. So, okay. So if you have, Z, if Z has a polar decomposition like this, like T to the V chi, where psi is like this unitary part and V is some element of H1 MR that's close to 0. Okay, you can just ignore this part here and you can focus on T to the V part if you like. Then the bimodule, phi restricted to Z, it's a single bimodule, corresponds to the symplectomorphism local system pair, war phi Z that I constructed at the very beginning. So corresponds to means it acts the way phi of Z would act, but I have some scarier notation for that. Okay, let's see. So I'm going to explain this notation. In other words, the Yoneda module of L convolution with phi restricted to Z gives you the Yoneda module of phi Z of L. Okay, so that's telling you that if you like for small symplectic isotopies, this is actually the Floer homology group that you would expect, like the Floer homology group of. Let me not say this at the moment. I'm gonna tell in a second. Here is the notation. HL is the right Yoneda module of L. It's well defined even if you don't put L to the Fukaya category. And I'm not gonna put it to the Fukaya category, but how does a quasi-functor act on something like this? It acts by convolution. So convolution is, as I said, it should be thought as the action of quasi-functor on L. But as I'm replacing L by its Yoneda functor, then I get another, another module. I replace L by its Yoneda module, sorry. And the corollary of the lemma is the following. Sorry. H star of this triple tensor product here is the Floer homology. So let me explain this maybe. So by the lemma, this part, oops, that's a bad color. Use a highlighter. By the lemma, this part is the same as this part. And when I take the tensor product over the Fukaya category with HL, Okay, this part is just abstract nonsense. I get, oops, sorry. This part is just abstract nonsense. Because, you know, if I convolve the right unit module with the left unit module, I get the Floer homology group, or like just the home set. If I extend the Fukaya category by L and phi z to the L prime, just to emphasize, I'm not extending it again, but anyway. So that's the quickest relation of this, you know, crazy algebraic construction to the actual family of symplectomorphisms. This triple tensor product gives you the Floer homology group. And that's only for Z close to the identity or close to the unitary elements. Okay. If you have any questions, feel free to stop me. I hope we will have some questions. So, you know, I also refer to this property here as phi being, you know, sorry, this capital phi restricted to Z being geometric, in the sense that it corresponds to an actual symplectomorphism. It gives you what an actual symplectomorphism does. It does what this actual symplectomorphism does. So, but you know, it's an informal term. And so observation is, you know, the simple observation is this triple tensor product is phi of Z here is restriction of phi to Z. Phi is like, you know, a family parameterized by a variety. I restrict to a specific point. HL prime and HL doesn't depend on the parameter here. So if I restrict the thing on the right hand side, then I get what I have here on the left hand side. And okay, this is a very bad point to pause. So you should now observe that this triple tensor product is a complex of modules over, you know, over the ring of regular functions. In other words, you can think of this as a, you know, complex of quasi-coherent sheaves over the variety here. It's by construction algebraic. You know what it means. How would it be analytic if you had an affinoid domain here instead, like a ring of analytic functions on a smaller annulus, for instance? You would have something analytic, but this thing is by construction algebraic. The problem is it may be gigantic, but it's not actually. You can use abstract nonsense that I'm not going to say anything about to show that this thing has coherent cohomology. Next, like it's cohomology and it's bounded, etc. So I'm not going too fast, right? Yeah. Questions? No questions. Okay. So this triple tensor product is our candidate for the algebraic sheaf, because as I said, the restriction of this thing to Z is the Floer homology groups of L with phi Z of L prime. So the candidate for the algebraic sheaf is this triple tensor product. And what we need is the lemma above, the Fukaya streak, and its corollary to hold for all Z. In other words, I want phi to act like, again, you should think this in heuristic terms, like as action of phi on L, and I want phi to act like a genuine symplectomorphism. But this should hold for all Z. I had the lemma for small z. I have to generalize this to all Z. Okay, so far nothing about group actions, and I'm coming towards that. Okay, so as I said, like, you know, we are replacing functors by a generalization, the bimodules or quasi-functors. And how do we convolve? How do we compose such things, the composition is replaced by the convolution. If you are familiar with Fourier-Mukai theory in algebraic geometry, for instance, that's what you do there as well. And the lemma is basically telling you that if the composition of the bimodules, capital phi restrict to Z1 and capital phi restrict to Z2, is the same as capital phi restrict to Z1, Z2 for all Z1 and Z2, then you have the property that you want. Then phi of Z act on L or H of L as the symplectomorphism phi Z. And the idea is actually pretty simple. I'm going to sketch a proof here, but before that, the idea is pretty simple. Like, again, I refer to this being geometric if it corresponds to the actual symplectomorphism phi of Z. In this case, it's phi of Z1. And this property that I stated here, I call this group-like property, or sometimes group action-like property. It basically tells you that this family of quasi-functors is a group action. And that means that if you know, phi of Z, oops, sorry, I don't know why. If you know phi of Z is geometric when you get close to the identity, and if you know this property also holds on an open neighborhood of identity, you can use this, highlighted part to actually show that the locus of Z where phi is geometric form an subgroup, an abstract subgroup, and an abstract subgroup of a connected algebraic group or a connected group that contains a analytic open neighborhood, basically contains everything. That's the basic idea. But for the sake of completeness, I'm gonna sketch a proof. Questions? Okay, I got very rare questions. The sketch of the proof is, for simplicity, assume Z is just T to the V. As I said, I'm taking these things from cohomology, but if you feel more comfortable, just think of the case where M is rank 1. So H1 of M is rank 1. So this is generated by a single element. So this is a genuine, element of Novikov ring, etc., instead of some element of H1M GM. And you fix an alpha such that V equals the class of alpha. Now consider the isotopy, the symplectic isotopy. Okay. So the lemma, by the lemma that I stated before, the lemma that uses Fukaya's trick is for for every Lagrangian appearing in this isotopy, you can pick a number, epsilon t, so that this relation is satisfied. Meaning, for any s that's smaller than epsilon t, phi of, phi, we can think of this as phi of s, act on the Yoneda module of phi alpha TL in the way you would expect by symplectomorphism. Okay, and now you can cover 0, 1 by finite domain of these intervals, and you can pick numbers T0 through Tk such that all two are adjacent, like so two adjacent Ti are in the same such interval. Okay, then the Yoneda, so forget about the word Yoneda, then H of phi alpha 1L is, okay, let me explain this better actually. I think I didn't write everything necessary here. So and by assumption, sorry, do you see me? Maybe you don't see me, hopefully you do, but oops. Make it green. So by assumption, this thing is H alpha T1L, right? And again, by assumption, T1 and T2 lie in the same small interval that we use, one of the same small intervals that we use to cover. And in this interval, this relation is satisfied here. Okay, I'm being a little sketchy here, to be frank, but in other words...
Well, it is a sketch of the proof, so it's fine.
Yeah. That's right, thanks. Yeah. But then you can apply this relation to the phi alpha T1L. And so you can get this T2 minus T1 added to here by T2L. Yeah, my handwriting is not extremely... My handwriting is okay. I just can't write in this program. Okay, and you can apply this iteratively to get this relation here. Okay, in the end you will get h of phi alpha 1. This doesn't require anything. This doesn't require any of the assumptions. This is something, okay, it's not completely true, but you know, you can't always write h of phi alpha 1 as a convolution of h of L with a single quasi-functor, single correspondence, whatever language you prefer. But you can always choose a sequence of, sequence of correspondences so that this convolution gives you the right thing. And okay, so if we are happy with this first step here, the second step is, you just apply the property I stated in the lemma to collapse everything here to everything, every phi here into a single phi t to the kv, and that's this thing. Yeah. If you have questions, feel free to ask. Because like there are 23 slides, but last slide is completely empty, and the second to the last slide is a thank you slide. So it's, and I can also skip the last, third to and fourth to the last slides because they are somehow extraneous. Okay. So what we need is this group action property. Okay. So this family is constructed in an artificial way. We know it is geometric when Z1 is close to identity. We don't know anything about its behavior when Z gets far from identity, whether it corresponds to a genuine symplectomorphism. And what I need to show is this group action property. And okay, as I said, this, like, the convolution should be thought as a composition of these correspondences. This is like, in a more geometric world, this would be geometric composition. So yeah, of two correspondences, but that's not what I'm doing. Okay. So the condition is basically saying that the family, okay, I said this as well. So the condition here is basically saying that family phi is an action of the algebraic torus. Okay, now I kind of feel, yeah. Hopefully this word quasi-functor is not more confusing than bimodule. The word, if you feel more comfortable, just use the word bimodule. Okay. So I need to show this, and so I will define a bimodule homomorphism, or you can think of this as a natural transformation if you want. How do I define? So if you are familiar with, again, Lekili-Lipyanski, this is geometric composition in kilted Floer homology. If you have two Lagrangian correspondences and define kilted Floer homology, how do you define, a map from the tensor product of the kilted Floer homology to kilted Floer homology for the geometric composition? So that's, this type of things, but instead of kilted things are what you need to count. In this case, I'm just counting ordinary disks. Okay, so I define this bimodule homomorphism by basically counting, by counting holomorphic disks where x1 belongs to here, x2 belongs to here, and now I weight them not by t to the energy, not only by t to the energy, and also z1 to the class of this guy, and z2 to the class of this thing. Okay, so that's like, yeah. So far I am. And some abstract nonsense, well, almost abstract nonsense, tells you that this is a quasi-isomorphism when Z1, Z2 are identity, or more generally when they correspond to unitary local systems. This is not quite abstract nonsense. This is a combination of abstract nonsense with slight abstract sense. And the goal is, I'm sorry, the goal is to show that this transformation F is a quasi-isomorphism everywhere. I think I'm in the most technical slide, but yeah, I still want to say this. So I'm just gonna summarize the steps here, but to be frank, the steps that I'm about to summarize are like the heart of the work. So it's kind of, you treat this as a dirty secret or whatever, but I think that's extremely important. So how do you do that? So you compute the deformation class of this family phi and con of F. So phi is like a family of transformations, right? Family of functors, if you want. And so it's con of F. And deformation class measures the rate of change. This is an entirely non-commutative thing. I don't think I can introduce it in the last few minutes anyways. But you should think of, if you are familiar with moduli of sheaves in algebraic geometry, you should compare this with Kodaira-Spencer classes of families of sheaves. Okay, so these two guys follow some specific cohomology classes. I mean Hochschild cohomology classes, but I bracketed the word Hochschild because I wasn't sure. Yeah, I mean, sorry, it's not because I wasn't sure. They follow Hochschild cohomology classes. It's just they come from actual cohomology classes in the way you would expect. Nothing very surprising. And these two are sufficient to imply that, okay, so we have a family here, right? A family parameterized by this variety, and this home, this relative home, is also a family parameterized by this variety. And the two bullets show you that this home set carries a connection, carries a connection. And okay, I'm also being slightly sloppy here, but because of this first line I wrote, it also vanishes at Z1, Z2 belonging to U of lambda. I'm sorry, belonging to the unitary part. It's because F is an isomorphism, so the con of F is 0. And abstract nonsense again implies that this thing here is coherent. So that implies the home set from like the home whatever. Okay, so if you have if you have a coherent sheaf over a variety with a connection that vanishes somewhere, then that means it vanishes everywhere. So it means F is a quasi-isomorphism, and it shows the group action property holds. Questions? Okay, I prepared a summary slide. I'm gonna summarize the main points. Okay. Yeah. Okay, so we start by constructing this algebraic family of quasi-functors. So this is somehow similar to family Floer homology. And Fukaya's trick implied that this is geometric for small z. In other words, it acts like a symplectomorphism plus unitary local system. And we wrote a transformation from this composition, or algebraic incarnation of the composition of quasi-functors to 5 Z1, Z2, and we show it's a quasi-isomorphism. That implies that this thing is like a group action. This family behaves like a group action, and that tells us that that we use this to conclude the family is geometric for all z. In other words, for all z, it acts like a symplectomorphism unitary local system pair. And from here, we can conclude this triple tensor product also has cohomology by the same reasoning that I explained. this has the same cohomology. This has the cohomology HF L phi Z of L prime at Z. So this proves the main theorem, and in other words, Floer homology groups fit into an algebraic sheaf. Okay.
Paris, maybe you can say a word about how this Fukaya trick actually works, because it might be that many people don't actually know this trick.
Okay, sure. Sure, I'm almost done. Do you mind if I actually postpone it to the end?
Of course, no problem. Absolutely.
It's like 3 minutes left. So I'm not going to say much about the other corollaries and applications, but okay. So I already stated some other corollaries of the theorem. Right, sorry, I already mentioned some corollaries of the first theorem. So another corollary is, this rank. You can consider the ranks of these Floer homology groups, and it defines an algebraic stratification of H1 and like H1 MGM, an algebraic stratification of this torus. In other words, you have a large Zariski open subset where this dimension is minimal, and a smaller local closed subset that's on the boundary of this open subset, and of the second minimal rank locus, and you can go on. So let me just state other applications. Okay, the second application is, well, an application like if you consider the stabilizer, it's in quotation marks. In other words, the locus of Z where phi Z of L is equivalent to L in some sense, then this also forms an algebraic subtorus of this algebraic torus. And this Lie algebraic is given by what you would expect, meaning like the classes, cohomology classes that die on L. And the idea is the following: is just to consider composition maps here, like L to phi Z to L, and composition maps also vary algebraically. So you consider the locus of Z where this composition maps hit identity. Let me not explain the details here. And just a quick note here is that the relation that I wrote here is slightly weaker than being a quasi-isomorphism, unless L is connected. Not, you can always assume L is connected. Okay, so this may be very well known. I don't know, like it's known that the flux group is all thing that flux group of something monotone, some monotone symplectic manifold is already zero. This can be thought as like a Lagrangian flux version. But if you have, if you have something, if you have an alpha such that phi alpha 1 of L is, well, is for instance Hamiltonian isotopic to L, then the restriction of alpha to L is zero. So I'm not presenting this as the most important correlate. It may be pretty well known as well. And there's an application to mirror symmetry, but I think I'm almost over time, so I'm not going to say anything about it. So thank you very much. Okay. So Octave's question. Let's see. I have a blank slide at the very end for the purpose of annotating. So, quite strict, right? Okay, I'm going to confine to, some simple case. So I'm on the question part at this point. I'm sorry, it's just to make sure I'm not going on the talk. Okay, but this is the simplest case. Okay, so let's say I have two Lagrangians like this, L1 and L2. Okay, L2 should have been blue anyway. And I wanna talk about, well, okay, that's not really the best example I have. Anyway, yeah, okay. I want to talk about the Floer homology group. Of HF L1 L2. Okay, in this case I'm going to deform L1. Okay, so this is like two generators. Let's make this Floer chain complex. This is two generators, right? Now, and it's just defined. Depending on your conventions, mu1 of x is equal to t to the area here. Times y. Okay. Now what I'm interested in is, let's use light green, is if I deform L1 a little bit, L1 tilde. Okay. So L1 tilde deforms L1, let's say with, I'm being very informal here, with flux, I don't know, A is the area here. Okay, so if L1 tilde deforms L1, sorry, my notation is, yeah, okay. How do I define the Floer, how do I write the Floer homology of L1 tilde with L2? Well, I can identify the generators, right? Okay, let's actually call this flux parameter, I don't know, T maybe? Forget about A, okay? But now the differential depends on the flux, right? On this parameter here. It's going to be T to the EU times T to the T, okay, here's just T to the T times Y. So in my case, I'm setting up the Z to be this T to the T term. So for small deformations of a Lagrangian, you can, somebody says something? Okay. You can get the Floer homology of the other closed Lagrangian by just deforming the weights in the Floer differential. And this deformation is going to be by the, T to the T, where T is a flux parameter. I don't know if that answers. Let's say. I don't know if that was explanatory. Okay.
Yeah.
More questions?
Sorry, that's yours.
I actually do have a little question. Earlier on, I think on slide 10, you mentioned a non-degeneracy condition in M, the symplectic manifold. I was wondering if you could say a little bit about that.
Sure. Sorry. 1 second. I'm trying to go to slide 10, but I think it may be more practical just to. I'm not able to go to slide 10. 1 second. 20. This is the first one?
Yep.
Okay, so you are asking the meaning of it, or you are asking why I do need that?
What is the condition specifically, first of all, and then where you use it?
So the condition that Mohammed uses, for instance, in the generation paper is can define the Hochschild homology of the span of Li here, or a span of a set of Lagrangians. And there's a, I forgot, open close map that goes to symplectic cohomology. Okay, and the image of this hits the identity. So open close map is, you count disks with one interior output and boundary inputs. Okay, and I don't know what's this. Okay, so the condition is this. This implies various things. So sorry, and you can also replace this in the compact case. It would be the QH, of course, not symplectic cohomology. One implication is it is generated by Li. The Fukaya category is generated by Li. Another implication is by Shields' thesis. The Fukaya category is smooth. It's a homological condition. It means the diagonal bimodule is perfect. And so I'm again like this. I'm using this generation here, and I'm using smoothness in lots of things that I referred as abstract nonsense. For instance, if you have a family M, like I didn't use the word M, right? Okay, if I have family phi here, it's a proper family, right? It's a, it's coherent.
Yeah.
Over, let's say, over this variety here, and so it's a trick, but like you can write equivalences like this, and you can use the resolution of diagonal. This is the same as phi itself, and you can use the resolution of the diagonal to actually show that this thing can be written as a as a complex of perfect modules.
Mm-hmm.
So this is like I claim things like from abstract nonsense it follows that this thing is a coherent sheaf, etc. This is basically that abstract nonsense part. And it shows up in other places too, like when I convolve, for instance, phi with phi.
Right.
I need to get something perfect as well. Where perfect means it's just like for instance, perfect is something that would imply its self-home sets are finite dimensional. Yeah, maybe this too. Yes, I want to black box thing this because it's maybe too algebraic, but
no, that's good. Thank you. Other questions?
I have a question.
sure.
So I'm not sure if that makes sense, but I feel like Zyda's representation kind of is included there somehow. You can define the Zyda's Lagrangian representation as an action of pi1 of Ham on the Fukaya category. And lots of things are a bit similar, like you get some Hochschild homology classes. And in any case, I just wonder if that kind of fits in that framework. And if yes, because you're considering symplectomorphisms, do you get the representation of pi1 of simp using that kind of language? And if you do, then do you have some computations of that?
Yeah, I haven't thought about this. I can see how. I don't think. Can you explain why this is Why would you expect this to give pi1 of simp? Sorry.
Well, you get an action of each simp on there, so why not take a loop of those and make them act and see what happens when you come back? Something along those lines. I'm not sure, like it's not very clear.
Yeah, so, but isn't like maybe there are different topological things, but isn't simp not mod ham basically the first cohomology? So do you actually expect anything different, or?
Maybe that's just what you're doing then.
I wasn't doing anything.
But for torus, it's not like this, right? So for two-dimensional, let's say.
What's that?
If you will take two-dimensional torus and you consider sim 0 mod ham, you get torus, right? As you presented basically on one of your first slides.
Yes.
Yes.
But I have monotone examples here. There's no flux.
So you see that in negatively, no, torus is also kind of.
But right? Torus was not an example of the theorem. The theorem held for negatively monotone.
Yes.
Or monotone. Yeah, it's a very fancy way of deriving that the flux group is actually, you can also use this as a very fancy way of deriving the flux group of such a thing as 0. But of course, this is not, I'm not presenting this as an application.
And back to Sarah's question, so when you formulated in this indeed a little bit algebraic way conditions of your Lagrangians, so if you have, let's say, surface of genus 2 and collection of curves, can you say in purely geometric terms, so which collections are kind of good?
For genus 2?
Yes, so surfaces of genus 2 and collections of curves.
Yeah, if I remember correctly, this was probably in one of Ivan's papers or something. I think Paul's paper also do imply like this generation. For Li, I mean, just a quick thing, this Bohr-Sommerfeld monotone condition, something that can be forced once you have the cohomology of M restricting to, the map from cohomology of M to cohomology of the Lagrangian. Surjective means that you can force this condition. But let's see. I think I'm taking, I forgot. I'm taking these Lagrangians and probably this, but I think I may need to add this one too. So the non-separating curves here. I mean the set of Li. Like in general, it's 2G plus 1 curves.
So here, does that actually generate the entire Fukaya category?
Yes, as far as I remember. I mean, again, this is like, I think this is one of, I think I made a reference for this at some point in somewhere, but yes, I would say. I mean, again, take this with a grain of salt. I need to check this again, but it's just, there are some references for this, yeah. I may also not need this one, but I did this anyways.
Okay, more questions? So maybe we just thank the speaker again now. And,